So what we've just done is looked at the principle of detection of gravitational waves. So gravitational waves can be detected by the separation or changes in the proper distance between 2 points. But what we now need to show is that you can actually generate gravitational waves which are going to be detectable. So essentially, again, I'm not going to go into the details, but energy momentum conservation gives the following. It gives you that the gravitational wave strain, is averaged over, is approximately the following. So G here is just the constant, R here is the distance to the source, I is the moment of inertia, and you'll notice this prefactor 2G, so G is 6.67 times 10 to the minus 11, right, it's a small number, and C, 3 times 10 to the 8 to the power 4. So notice, importantly here, this prefactor is a tiny number. And then, of course, the distance is an astronomical distance, so the distance is a large number. That makes it even smaller still. And then, basically, this is the second derivative of the moment of inertia. So you can only do so much to change your moment of inertia. And so things with small changes in the moment of inertia will do rather little. That's just the integral of the density times the xi, xj, dv. Now, of course, if your moment of inertia isn't changing, as we've noted, a perfect sphere rotating, for example, then you don't get any radiation. You only get this in a quadrupole scenario. So this is the moment of inertia tensor. Or the quadrupole tensor. So let's think about how you might actually get your maximum amplitude out. And that's going to be something where the moment of inertia changes a lot and a real astrophysical system. So let's look at two equal masses, mass m, separated by some separation. So 2 stars, mass m, separation a. Ixx is just rho x squared dv, which is equal to 2m a over 2 cos omega t squared, which is equal to 1/4 ma squared 1 plus cos 2 omega t, just multiplying and using the double angle identities. I can then differentiate that twice. And I get that hxx is equal to 2gm a squared omega squared over c to the 4r cos 2 omega t. So the first thing to notice, of course, is that the amplitude of the gravitational wave varies with the phase of the orbit. So these are wave-like solutions, they come and go. But also to note the 2 omega t in here. The gravitational waves have twice the frequency of the source. And then, of course, the amplitude, or the maximum amplitude, is just setting the cos 2 omega t to 1. So it's gm a squared omega squared over c to the 4r. And there's some important things to note in here. Okay, so remember using Kepler's third law. Okay, omega squared is just g m1 plus m2 over a cubed. And so, if, for example, I wanted to look at two black holes with 10 solar masses separated by a solar radius at the galactic centre, then you'd have a period of about 38 minutes. So, two black holes, two 10 solar mass black holes at galactic centre. Which is 8 kiloparsecs away. Then P equals 38 minutes, and H is about 2 times 10 to the minus 21. Sorry, here A is 1r solar. So this is a tiny, tiny change. Right, this is delta L over L. Remember? So it's less than 0.1 millimeters over, 5 parsecs or something like that. So this is where the statement comes from, that the distance from us to the nearest star needs to be measured to the accuracy of a human hair in order to detect gravitational waves. And so when you first look at this, you think this is going to be impossible. You think, how can you possibly measure distances that accurately? And so, part of the discussion early on in gravitational waves was whether or not you could actually ever generate them with a strength that could be detectable, and then whether you could ever build such a sensitive detector. And it looks pretty hopeless, but it is possible. And in particular, this is one thing, but you can see here, if I have sources which get much closer and therefore much higher angular frequency, and push up the mass as much as I can push this amplitude up somewhat more. So, massive objects in short period orbit are the best sources. The angular frequency omega becomes very high, and that goes up faster than A shrinks. Also note, the amplitude is proportional to 1 over r, not 1 over r squared. And so if I was looking at electromagnetic light, I measure a flux per centimetre squared per metre squared. Here I measure a strain. And that's an interesting feature because it means as I make my gravitational wave detectors more sensitive, if I double the sensitivity, I see twice as far away, or 8 times the volume, rather than the square root of 2 further away, which I do with an electromagnetic telescope. And so it's an important point that if I improve my sensitivity, I can see further away. So it might actually be, ultimately, remarkably, if I can make gravitational waves sensitive enough, that they're some of the best probes of the distant universe, rather than EM light. And then a very final point, and this perhaps is the most critical point for detection, gravitational waves, they bend space-time, they carry energy, and actually angular momentum, and therefore they cause an orbit to shrink. And what that in essence means is that as a binary star, or even the Earth around the Sun, goes on, it loses energy in angular gravitational waves and will eventually merge. And the timescale for that for the Earth around the Sun is some ridiculous number of Hubble times. But for two black holes at a close separation, it can actually be quite small. So stars will therefore merge. In particular, binaries with neutron stars and black holes.